All right, we're back. We are on page 5 of notes 4 of Calc AB. We're talking about differentiability, continuity. We know that differentiability implies continuity. We know that continuity does not imply differentiability. We also know that not continuous implies not differentiable. I feel like there's a fourth choice in there somewhere, but like I don't really care what it is. Those are the ones you need to think about. Differentiability implies continuity. Continuity does not imply differentiability. And then not continuous means not differentiable. There's got to be a fourth one, right? Because there's like, whatever. All right, let's see if we can do this problem. So for each of the following, find values of a and b that make the function differentiable. Okay, so let's think. Differentiability implies continuity. So to make something differentiable, we also definitely need to make it continuous, because otherwise you run into this weird scenario where you could have a function that kind of looks like this, and then like this, right? So if all we did was look at the derivative of this thing, other than at that weird point, the derivative is always going to be the same. So we might think that this function is differentiable, but it's not even continuous. So there's no way it could be differentiable. All right, so that's a big idea. And the reason I highlight that is that we're going to have to force the function to be continuous, which means we need the limit to exist, the function to exist, and the limit to equal the value of the function. Once we do that, we'll take derivatives and kind of almost do the exact same thing. So let's get into it and see what happens. All right, so I'm going to make it continuous, which means, so f of 2 is equal to the limit as x approaches 2 from the left because of the definition, right? So the definition that we should use is this one when we're talking about from the left. So from the left of f of x, which is the limit as x approaches 2 from the left of x squared plus ax plus 2. And then that limit we can do by straight evaluating, because quadratics are continuous because they're polynomials. And if a function is continuous, you can evaluate the limit by direct substitution. So 4, 6 plus 2a. So 6 plus 2a. Okay, so that's the value of the function, and it's the limit from the left. So I just need to find the limit from the right and then set those things equal. And that'll be continuity. So we're dealing with continuity right now. So continuous. That doesn't look good. Let's see. So let's say make it continuous. Still, like, my handwriting is never going to look good. So let's just move on and say that we did that. The limit as x approaches 2 from the right of f of x, because I always like to do it with the notation first and then go back and do it with substituting in. You're trying to make this readable to people, right? Like, it's not about like, oh, can you just hack your way through it? Like, no, you want it to look good. All right, so this gives me 6 plus b. Okay, so we need the limit. I almost certainly did not give you enough room, by the way, and I apologize for that, especially because now I'm trying to also cram it in. Like, jerk move on my part. I can move this a little bit, but of course you can't do that, so still a jerk move. Okay, so if the function's continuous, we're going to have 6 plus 2a equals 6 plus b. So we know that 2a equals b. Good start. Okay, that's one equation. Now the differentiable part. So what we do for this is we're going to find f prime. So f prime is going to be piecewise, though. F prime of x is going to be, all right, so we're going to take the derivative of the upper branch, I guess, and get 2x plus a, power rule, all the way through. So 2x plus a, but that's only valid when x is less than 2. So we drop the equality, because until we figure out if we can make it differentiable, we don't know if the derivative even exists at 2. Like, we're trying to make it exist at 2, but maybe it won't work out. From the second branch, we just get 3. And that's going to be when x is greater than 2. Okay, so if this thing is differentiable, then the derivative needs to exist at x equals 2. And we also want the limit from the left to equal the limit from the right. So we basically want the derivative to be continuous. it's a weird fact that derivatives don't need to be continuous. I don't want to think about it or talk about it right now, but like, it's a thing, right? So like Google that concept. Do derivatives need to be continuous? Or like look up the example. The example that you'll find, I think, is going to be like x times sine of 1 over x, or x squared sine of 1 over x, something like that. I'll be honest with you, I do not follow the logic. Anyway, let's do this. So this tells me that 4 plus 4a, nope, 4 plus a. 4 plus a from the top branch needs to equal 3. So a should be -1. Now if a is -1, then b is equal to twice a. So b will be equal to -2. And so we're saying that if this is true, I feel like I should use a different color for that. I didn't grow up taking good notes. It's my fault. Like I wish that I wish a lot of things. I wish I had better handwriting. I wish I better knew how to take notes. Just like so many things. All right, so what I think would be interesting is to look at this. So let's see if we got it right. So I'm gonna go to the calculator and let's see. So who knows what we were doing there? Calculator pit, I'm gonna use a graph page. And I'm gonna graph the piecewise function using the values of a and b that I found. So it'll be x squared minus x plus 2, and that's valid when x is less than or equal to 2. Less than or equal to for you is control equals and then like pick it out, just faster to type it. And then 3x minus 2 when x is greater than 2. This is a nervous moment because if it didn't work, we got to go back and fix things. Let's see what this looks like. That definitely looks like a nice continuous differentiable function. Let's look at what the derivative looks like. I don't actually know what's going to happen here. So let's just go for it. I want the derivative of f1 of x. There you go. Oh, look at that. That's cool. So the derivative changes from increasing to constant, but the derivative exists at that point, right? The derivative itself is not differentiable, but that's not necessary. We just need the derivative to exist at x equals 2. And it does. That's pretty neat. So we did it. So these values of a and b give us a nice, smooth, continuous function, differentiable and continuous. Let's go back and do the next problem. And then I'll probably like wrap up this video and come back and do more because this is what we do now. I don't know if I mentioned it. I probably mentioned it. So I'm making all of these while I'm social distancing and like what is it? Self-quarantining or whatever during the COVID-19 outbreak. So I got a lot of time, so I'm making a lot of videos. So let's keep going. All right, so same logic here. We're gonna need, so where is it that G of 4? Where does that come from? That's gonna come from the upper branch because of this part. Oh God, that's not a highlighter. Maybe I'll use the same color though. I never really highlight in this color. Ooh, it's not bad. It's like it's a worse looking marker or whatever. I think of them as dry erase markers because that's what I used to use for this. All right, so let's make it continuous. Continuous. We need f of 4, which will equal the limit as x approaches 4 from the left of g of x. And that'll be the limit as x approaches 4 from the left of, this is a weird function, 9/2 plus a x minus 5 squared. And this is going to be equal to, can I scroll over? I can't. Can I pick things up and move them? I bet I can. Let's move that over. So that's going to be equal to, direct substitution gives me 9/2 plus a. So 9/2 plus a. And then I need the limit as x approaches 4 from the right of g of x. So I'm going to use the other branch for that, which has a natural log, which I'm not really nervous about because, I don't know, natural logs, they're not as bad as people make them out to be. Natural log of x minus 3 plus b. So this is the natural log of 1, which is 0. You should review your natural logs every once in a while because you're going to need to know quite a few things. Properties of logs are going to come up. The graph of natural log is super important to know. There's a lot of stuff. This is just straight up b. Okay, so therefore we get an equation out of this. So I'm going to squeeze it in here. Therefore, 9 over 2 plus a equals b, right? So that'll force the function to be continuous. That's the relationship between a and b when the function is continuous. Now the issue is, can we also make it differentiable? So differentiable. And we're going to just find g prime as a piecewise function, and then see if we can come up with a and b that make the branches of this piecewise function come together at all. They don't have to come together nicely, they just have to come together. So I think maybe we'll be able to do it. All right, what's the derivative of the upper branch? Well, 9/2, the derivative is 0. Then I'm going to like chain rule, power rule, chain rule situation. So I'm going to bring the 2 down, subtract 1, and I'm going to multiply by the derivative of x minus 5, but that's just 1. So I'm going to get 2a on the x minus 5. And that's going to be valid when x is less than 4. Not less than or equal to yet, because I don't know if I'm even going to be able to do it. Like maybe I'll be able to go back and fill it in, but maybe not. The derivative natural log is of u is 1 over u times the derivative of u. So in this case, 1 over x minus 3 times the derivative of x minus 3, which is 1. So just 1 over x minus 3. 1 over x minus 3. Knowing how to take derivatives is going to make your life so much easier. Like go practice those. If you have not practiced those enough to be able to do these like relatively quickly, go do that. All right, so we're interested at x equals 4. So at x equals 4, we get negative 2a from the top branch, and we get equals 1 from the bottom branch. That's pretty nice, because that means that a is negative 1/2. And if a is negative 1/2, and we know I'm like unable, I can't change from my marker. That's weird. What is that? I wonder if it's my stylus. It's like a brand new stylus. Okay, I can double click. Can't do it. Can't get a highlighter. Okay, so this thing is true. Oh, you know what? I can't do anything. Hold on. Oh man. What am I gonna do? Can I still write? I can still write. I'm just gonna finish the video. I can't actually scroll the screen, but I have enough space. So if a is equal to negative 1/2, 9 over 2 minus 1/2 is 8 over 2 is 4. So I'm gonna say b is equal to 4, and I will do this. Hopefully I got it right, because I've crashed this, so I don't really know what I'm gonna do to get it to work during this video. I am going to switch over to the calculator and see how these values kind of like stack up. So I'm going to doc for, let's put in a new problem and a new graph in a new problem so that we can start step 1 again. So this will be piecewise function, piecewise. All right, so 9/2, and then a is minus 1/2. And then x minus 5 squared, and then that's when x is less than or equal to 4, and natural log of x minus 3 plus 4, I guess, when x is greater than 4. And yeah, I got nothing to complain about there. That looks smooth. I can't even tell where the transition is, so that's even better. Let's look at the derivative. You should use the template. It's just a little faster for me to type. I don't even actually know if that's true. I just always do it. Oh, look at the derivative. It's pretty weird. It like goes smooth, like linear, right? Because the derivative of quadratic is linear, and then all of a sudden it's like weird. It turns into that reciprocal function. But like it doesn't need to do it smoothly. It just needs to connect perfectly. And it does, right? We need the derivative to exist. We don't need the derivative to be differentiable. And I don't even know if it is, and we're not going to find it out because I've crashed the app that I'm using and I can't go back to it. So I will try to go back to the screen and see what it looks like. And maybe like something magical has happened. Maybe like just by switching it up, it will suddenly work again. Nah, wishful thinking, not happening. All right, so I'm going to stop the video here. I'll come back hopefully in another video with this thing working, and we will keep going. So I will see you then.